The second part of this unit, we are going to be looking at vectors. A vector is a ray, which you learned about in geometry. It starts at a point and continues in one direction. Two things that define what a vector is are magnitude, which is how long the vector is, and direction, which is where the vector is headed. So for magnitude, we will use the distance formula, and for direction, we use the slope formula. Also notice the notation for magnitude. You put the vector in the middle and two bars around it, and that tells you that you're talking about the magnitude of the vector. We have several different parts to our vector. We talked about the initial point is where the vector starts, the terminal point is where it ends, and then the distance along the x-axis and the vertical distance give you the x and the y component. You can also express the vector in component form. You use pointy brackets and you put the x distance, the horizontal distance first, and the vertical distance second, almost like you're creating an ordered pair. To name a vector, you start at the initial point and the arrow goes towards the terminal point. You can also name a vector with just a single letter, and we will write it in bold. Since as a student it's hard to write in bold, you could either make the line thicker since you have that option on Notability, or you can just put the arrow above it to denote that you're talking about a vector. It's helpful when our vectors are in standard position if they start at 0, 0, and because all vectors with the same magnitude and direction are considered equal, we use vectors in standard position quite a bit. The first example, we're going to practice finding magnitude and direction for two different vectors, and we will see whether or not they're equal. Both the magnitude and the direction have to be the same for the two vectors in order for them to be considered equal. We'll start off with the magnitude of vector PQ, and that is found using the distance formula. Distance formula, remember, is x2 minus x1 squared plus y2 minus y1 squared. Subbing in those ordered pairs, we have 3 minus 0 squared plus 2 minus 0 squared. 3 squared is 9 plus 4 gives us 13. So the magnitude of vector PQ is the square root of 13. And then we'll find the direction of PQ by finding the slope of the line. I will just call this slope of PQ. Slope formula, remember, is y2 minus y1 over x2 minus x1. We get a slope of 2 minus 0 over 3 minus 0, or 2/3. That's the direction of PQ. We need to do that again for RS to determine if they're equal. As I am out of room, I'm going to erase this to start over, so make sure you pause now if you need to get any of this down. Finding the magnitude of vector RS. We take our x values and subtract them, 4 minus 1 squared, plus our y values and subtract them, 4 minus 2 squared. 3 squared is 9, plus 2 squared is 13, so we get a magnitude again of the square root of 13. So far, the vectors appear to be equal, but they must have the same direction as well, so we have to find the slope of RS. Again, change in y over change in x gives us a slope of 2/3, which is the same direction as vector PQ. So even though these vectors have different initial and terminal points, they have the same magnitude or length and the same direction or slope, so they are equal vectors. Part B is asking for the component form of the vectors. So we need to find the distance along our x-axis and the distance along our y-axis. We actually found those when we calculated the slope. It was just upside down. We had change in y over change in x, and when we write component form, the change in x goes first and then the change in y. So for both of these vectors, because they are equal, our component form will be the same as well. Looking at component form and magnitude again, this time our vector is going down, so we will have a negative component form for y, but a positive direction because we're heading to the right for x. So the component form for this vector is a positive 8 in the x direction and a negative 2 in the y direction. Because the distance formula, it doesn't matter where on the graph it is. For ease, I'm going to call this point 0, 0. I will put this vector in standard form. So this would be the point 8, negative 2. To find the magnitude, we set up our distance formula. Because this vector doesn't have a name, I will just call it u. And we're looking for the magnitude of vector u. Distance formula will be x minus x squared plus y minus y squared. 8 squared is 64, plus 4 gives us the square root of 68. And because the square root of 68 can be simplified, 4 is a factor of 68. The square root of 4 is 2. And 4 times 17 is 68, so we have 17 left over, which gives us a magnitude of 2 times the square root of 17. Next, we'll find component form and magnitude given 2 points instead of a graph. To find the component form, we'll call this vector v. You do change in x, comma, change in y. You have to start with that terminating point. This gives us a change in x of 12 and a change in y of 4. So there's the component form for this vector. Once again, setting up distance formula for our magnitude. We have change in x squared plus change in y squared. Twelve squared is 144, plus 4 squared is 16. We get a square root of 160. 160, of course, has a perfect square factor of 16. The square root of 16 is 4, and 16 times 10 gives us the 160. So our magnitude is 4 times the square root of 10. I have decided to bring the U-Try questions back on this one, as I feel the assignment should go fairly quickly, and it will give us an idea of where to start right away when we do our warm-ups together.